Welcome back to new series in auto tech, i.e. model-based development. That's how we launch a new series here at the Deep Dive. And today we're tackling, well, the methodology that really underpins almost every advanced vehicle you see now, model-based development, or MBD. If you're working with complex embedded control systems, think ADAS, battery management, anything like that, MBD isn't just, a nice to have. It's pretty much standard practice these days.
Absolutely. Our mission today really is to take all this documentation and boil it down to the essentials. We need to get clear on what MBD actually is, how it's different, fundamentally different from the old ways of doing embedded software. And crucially, why tools like MATLAB and Simulink have become, well, almost the universal language for this whole approach.
Okay, let's start with the why. What was the big problem MBD came along to solve? Looking back at traditional embedded development, it was very linear, wasn't it? Requirements, then design docs, then someone manually codes it, and then you test on hardware.
Yeah, and that sequential flow, it was frankly a ticking time bomb. Imagine designing a whole building on paper, hiring everyone, starting construction, and only then finding a major flaw in the foundation. The core issue was late-stage error detection, finding bugs, or maybe realizing you'd misinterpreted a requirement. After you'd coded everything and had hardware, it meant huge delays. Redesigns, recoding.
And huge costs, especially when physical prototypes were involved.
Exactly. Exorbitant costs.
So MBD flips that script. It says, let's move validation way up front, right to the beginning of the design phase.
That's the fundamental shift. MBD makes the executable model the single source of truth, the central point for everything. This model isn't just a picture, it actually runs. It represents the controller logic and the physical system it's controlling. So you can simulate and test how things will behave months, even years, before you have actual production hardware.
Okay, so if the model is now central, that must change the underlying principles of how you work. What are the key ideas that make MBD so different, maybe revolutionary for engineers learning it?
We can break it down into about 5 core principles. First, like we said, executable models as the source of truth. These aren't just vague text documents anymore. They're precise, mathematical, runnable representations of both the plant, the physical system, and the controller software.
That sounds like it forces different teams, like controls engineers and software developers, to speak the same language.
It does, precisely. They're both working with the same visual executable artifact, and that flows right into the second principle, simulation-based verification. Because the model runs, you can test your control algorithms, your system dynamics virtually. You can run thousands of scenarios, different conditions, almost instantly, long before you need expensive hardware prototypes.
Right, okay. And once you've simulated and tweaked that model until it's behaving perfectly, then comes maybe the biggest impact for actual production software. Principle 3, automatic code generation.
Yes. This is where MBD really tackles risk head-on. Tools, mainly embedded coder in the MATLAB Simulink world, can take those verified graphical models and translate them directly into optimized C or C++ code. This just bypasses a huge source of bugs, simple human error, when translating complex algorithm logic into lines of code manually.
So if the model's behavior is verified, the code that pops out should be, well, functionally identical. That seems critical for safety systems. We have standards like ISO 26262.
Absolutely essential. You need that predictability. Which brings us nicely to the fourth principle, continuous testing and traceability. MBD isn't just about the model, it's about linking everything together. You maintain connections, bidirectional links between every part of the model, the original requirements, those tech specs we mentioned, and all the test cases you run. This traceability is non-negotiable for standards like ISO 26262. You have to prove where every piece of code came from and that it's been tested against a requirement.
Makes sense. And the last principle, MBD isn't a rigid one-shot process, is it?
No, definitely not. The fifth principle is iterative refinement. It's designed as a cycle.
Yeah.
I model something, you simulate it, you analyze the results, and then you refine the model based on what you learned. It allows for really rapid iteration. You find out quickly if your control loop isn't performing right. You don't wait 6 months for a physical test.
Okay. That iterative cycle, heavy on verification.
Mm-hmm.
It sounds like it fits perfectly with the V model, that sort of standard framework for complex system development. How does MBD actually work within that V model structure?
Yeah, MBD really provides the engine and the artifacts that make the V model practical for complex software. The V model fundamentally splits development into 2 sides. You've got the left side, which is all about refinement or breaking things down.
Decomposition, right? Starting high level and getting more detailed.
Exactly. And then the right side is validation and verification, or V and V, where you put things back together and check that each stage meets its goals.
So walk us down the left side first. We start with high-level needs.
Right. You begin with system requirements. Things like the adaptive cruise control must keep the speed at 100 kilometers plus or minus 2% under these specific conditions. These usually live in requirement tools, maybe Simulink requirements itself, or something like IBM doors. As you move down the left leg of the V, you break those down into functional designs, component architectures, detailed module designs.
And the MBD artifact here is the model itself being built.
Precisely. You're creating that executable model, often using Simulink for the system dynamics and maybe Stateflow for the complex decision logic, the supervisory control. You're defining the algorithms, getting them ready so that when you hit the bottom of the V, the code generation step produces code that meets standards like NSRAC for coding style, or fits into an AUTOSAR architecture for standardized software layers.
Okay, so design refined, model builds, bottom of the V, autocode generation happens.
Yeah.
Then we start climbing the right side V and V. And this is where simulation testing really takes over from manual testing and where we hit that alphabet soup of testing acronyms.
Yes, the loop acronyms. They're the everyday language of MBD testing. And the beauty here is the sequence. You test the model concept first, then the code generated from it, then the code on the actual target hardware, all based on that same original verified design. This step-by-step virtual testing is what builds confidence and, crucially, saves enormous amounts of time and money by catching errors early.
Let's unpack them then. What's the very first simulation stage?
That would be MILO, or model in the loop. This is pure functional testing. You're running your controller model against your plant model, checking the math, the logic. Does the basic idea work? Does the cruise control algorithm in simulation actually maintain speed?
Okay, so MIL-L proves the design concept is sound. But just because the model works, how do we know the code generated from it is okay? That the CC++ translation didn't introduce errors, or the compiler maybe optimized something weirdly?
Good point. That's the job of SIL, software in the loop. Think of SIL as unit testing for the auto-generated code. You take that CC++ code, compile it, and run it in a software environment, often on your development PC. You feed it the same inputs you used in MIL-L and check if the outputs match exactly. It verifies the integrity of the code generation toolchain itself.
And the key benefit here is still no hardware needed, right? Purely software testing.
Exactly. Still virtual, but there's always a but. The code might run perfectly on your powerful development PC, but the actual target ECU, the microcontroller in the car, is often much more constrained. Different memory, different processing quirks.
So just because it works in SIL doesn't guarantee it works identically on the actual chip.
Right, which brings us logically to PIL, processor in the loop.
Okay, processor in the loop.
HEDL bridges that gap. You take the same generated code, compile it specifically for the target processor, and actually load it onto that physical chip. But, crucially, the inputs and outputs, the environment around the chip, are still simulated by your computer, by the modeling environment. So you're testing the algorithm's timing, its memory footprint, its real behavior on the intended hardware, but without needing the rest of the car.
Okay, makes sense. We've tested the design concept, MIL, the generated code itself, say LAL, and the code running on the target chip, PIL.
What's the final step, the big integration test?
That's AAL, hardware in the loop. This is the closest you get to the real vehicle without actually being on the road. It's the final system integration check. You take the actual physical ECU, the final hardware box with the finalized code loaded onto it, and you plug it into a specialized real-time simulation rig. Systems from companies like DSpace or SpeedGoat are common here. This HEAL simulator mimics everything else in the vehicle in real time, the sensors, the actuators, the engine dynamics, the network communication. So the ECU basically thinks it's in the car doing its job. And you can bombard it with realistic scenarios, fault conditions, test its limits.
Exactly. You're testing its performance and robustness under stress.
The huge advantage running through all of this seems to be that early fault detection. Finding a logic error in Miligallo costs what? Maybe a few minutes of an engineer's time?
Pennies, relatively speaking.
But finding that same bug during hill testing, or worse, during a vehicle test drive, the cost just explodes, right? Redesigns, hardware changes, program delays.
Oh, absolutely. It's exponentially more expensive and time-consuming to fix a bug late in the game, especially once hardware is involved. Fixing it in a graphical block diagram is easy. Fixing it on a soldered board in a prototype car is a nightmare.
And that really underscores why the tools enabling MBD, like MATLAB and Simulink, are so central. The whole process relies on what they can do.
It does. They form the platform for this entire workflow.
Let's clarify their specific roles, because they aren't quite the same thing. What does the base MATLAB environment handle in MBD?
Right. MATLAB is more the high-level text-based environment. It's really strong for analysis, data handling, and automation. A key role is in algorithm development, especially early on. Engineers often use MATLAB's rich mathematical functions to quickly prototype complex algorithms, filters, estimators, control laws before they even start building blocks in Simulink.
So it's like the mathematical sandbox for trying ideas out. What about all the tuning parameters and calibration data?
That's another huge role for MATLAB, parameter management. It's often used as the central place to store, manage, and analyze calibration data. You can script MATLAB to tune parameters automatically during simulations. And beyond that, MATLAB is the scripting engine. It automates repetitive tasks, running batches of tests, generating reports, connecting the MBD process to continuous integration pipelines using tools like Jenkins.
Okay, so MATLAB handles the data, the analysis, the automation around the model. What about Simulink itself?
Simulink is the graphical heartland. It's the block diagram environment. Its primary role is system modeling. This is where you visually represent the system's dynamics, the mechanical parts, electrical components, hydraulics, whatever, as interconnected blocks. You build the virtual representation of how the physical system works.
And the control logic lives here too.
Yes, absolutely. Control logic development happens in Simulink. This often involves using Stateflow, which is part of Simulink, for building state machines. Think about managing different operating modes like on, off, standby, fault for that cruise control, or handling complex decision sequences. Stateflow is brilliant for visualizing and implementing that kind of supervisory logic. And critically, Simulink is where you configure the interface to embedded coder, setting up how the model translates to that high-quality, standard-compliant CC++ code we talked about earlier.
So putting it together, MATLAB is for the high-level math, data wrangling, and scripting. Simulink is for visually building and simulating the system and the control rules, ensuring that what gets generated as code is solid because the model it came from was thoroughly tested.
Exactly. That systematic verification is the key to improving quality and drastically reducing those late-stage human-introduced coding errors. If you step back and look at the big benefits, MBE definitely leads to accelerated development because you can iterate on designs so much faster virtually. It leads to improved quality by catching errors early and automating code generation. And, maybe underestimated sometimes, enhanced collaboration. Having that central executable model means different teams, controls, software, mechanical, electrical, are all working from the same page, quite literally.
That collaboration point feels really significant, especially with modern vehicles being so complex. That central model must also enable incredible reusability, right? You could take a verified model for, say, an ABS component and potentially reuse it across different car platforms.
Absolutely. MBD is built for that kind of scalability. You develop and verify subsystems, functional blocks, and then you can potentially reuse them, combine them to build much larger, more complex systems.
Which brings us to a really interesting point for you, the listener, to think about.
While MBD offers this amazing potential for building vast systems from reusable, verified blocks, what new challenges do engineers face when they try to integrate dozens, maybe hundreds of these modular subsystems across many different ECUs in a really connected vehicle architecture? The complexity doesn't just vanish, maybe it shifts. It shifts towards managing the interfaces, the interactions, the integration of all these pre-verified pieces. That integration puzzle, that's a huge focus now.
A fascinating challenge indeed. And that integration question is definitely shaping the next wave of automotive engineering.
Thank you for watching video. Now we will meet on part 2. For more videos, do like, share, and subscribe to our channel.